Okay. I have to say that Alan from the keynote was right. Like the lights on the face are a bit annoying. Well, thanks everyone for being here today. Actually, going back to the keynote, I really like the keynote, and I hope that what I'm about to show you today will give you a chance to cut some slack on your work and you are able to go home earlier. So my name is Flavio. I'm CTO at Qbeast. My background is primarily distributed systems, but in the recent past, I have been doing more and more work in the data space. Started with like stream processing, and in the past 2-3 years, I've been looking to data lakehouses. So today, I wanted to talk a little bit about what I learned throughout that journey, and in particular, what I've been focusing on in my new gig at Qbeast. So let's get going with that. I do not expect to be a surprise to anyone here that data lakehouses, that whole discussion about data lakehouses, what they mean, architecture, is a hot topic in the market today. There are lots of users, customers, whatever you wanna call them. Looking into data lakehouses, implementing data lakehouses, and I picked this number, 95% of respondents of one survey that Dremio, the company Dremio did, on the state of the data lakehouse, saying 95% of their respondents expect to have at least 25% of their workloads running in a data lakehouse. That matches my expectation. Even if you do not believe on the exact number, whether that's 95 or less or more, it is an indication that the market is going in that direction. There will be more and more cases we should expect running in the lakehouse. But let's talk a bit about why that's the case. So what is the gist of the lakehouse architecture? It's not a surprise that this is an extension of the data lake concept. So in a data lake, what we traditionally have done is put our raw data in this decentralized repository. Why is that interesting? Because I typically implement that with a distributed file system, an object store. I can store anything I want in there. With any format, any native format, I can create my formats and store it there. The thing is, for structured data, the capabilities that you could get out of the data lake directly were limited. And so there was still, for a lot of users, there was still the need of relying on other database technologies, database data warehouse technologies, to resolve their workloads. So the whole data lakehouse movement is a wish to bring more of those workloads to the data lake. And the goal, quite frankly, did not change that much. We want to have a central repository rather than having to have ETL jobs like copying data from one place to the next, moving data, and so on. I don't know if, how many of you have had a chance to look at an ETL map from a large organization, but you can easily have hundreds to thousands of ETL jobs going on in parallel. And so reducing that and ideally even eliminating that altogether is a pretty good goal, and this is one of the promises of the data lakehouse concept. Now, along with that, one of the enablers of the data lakehouse is this new generation of open table formats. So before, or for many years, we have had Hive. It was a great idea. It allowed us to have an open table format against a data lake, but it was limited in a number of ways. And so there is this new generation with Apache Spark, Delta Lake, Hudi, that allows us to bring more of those data workloads into the data lake. So what are these open table formats about? The idea of the open table format is to very easily put this metadata layer on top of files and give you this table abstraction on top of files and objects. Then query processors will work with that metadata to decide what data to process. If you're trying to update a table, how to update the metadata and the set of files that go along with it. So this is what the open table formats are about. And I'm putting here just a couple of examples Apache Iceberg and Delta Lake, how they organize their metadata. So in Apache Iceberg, you have this hierarchy starting from a catalog and then a set of files, metadata, manifest files. In Delta Lake, you have explicitly a transaction log. So there are JSONs with entries, adding, removing files. And at the bottom for both of them, we have just the files themselves, files and objects. And this could be Parquet files, ORC files, and such. But then how do these query processors work with these open table formats? Well, so the query processor is going to look at the metadata. So if you're trying to execute a query against a table, the processor is going to look at the metadata and decide which set of files it needs to go look at. But it's not only that. It provides, for example, in addition to that information about files, provides statistics about the files, which are very important for query performance. So min-max file filtering is a technique that is very often used by processors to reduce the amount of data that they need to process. This idea of min-max filtering, which is actually something that I'm going to focus quite a bit on throughout the talk, is not really a new idea. Has been around for a while. Quite frankly, I don't know the exact origin of this, but if we, tracing back a few pointers, like I find in academic work references from, I don't know, there's this paper from 2018. There was even an earlier reference that I found from 2014. If you go to the Parquet code, I see commits from 2014. So again, not really a new idea. But what is perhaps not entirely explored is how do we organize the data so that we can exploit as much as possible this min-max file filtering mechanism. And I want to walk you through a very, very simple example just to get a sense of the idea I'm trying to convey. So what does it mean to reorganize the data and be able to have more effective min-max file filtering? So let's say that I have this one table with two columns, a column A of integer values and a column B with double values. And this is my present state of the table, yeah? So I have 4 files. Each file has only 2 records. Again, I promise that the example is going to be simple. And I have the values that I'm showing you on the table. So for each of the files, I'm also putting the min-max ranges for each one of the 2 columns. Now, if against this table, I execute a simple filter, then because of the way the data is arranged, I essentially have to read all files. Okay, so if I just look at the min-max ranges to try to filter, I won't be able to filter out anything. But now, if I reorganize these records, for example, by looking at those 2 columns as dimensions of a 2-dimensional space, and now I split the space 4 ways, and I associate each one of these quadrants to a file. Now, all of a sudden, I don't have to read all files anymore. I just have to read one. So with that, I'm reducing the amount of data that I have to read, the number of files I have to read from 4 to 1. Of course, I'm not making the promise that if you do this, every time you're going to be able to read just one file. The example is crafted so that I come down to that. But in practice, if you try that with real data, you do get real benefits. Not necessarily one file, but you do reduce substantially the amount of data that you have to read and process. The other important point is with these tables, they accept transactions so that you can change the table, right? So you assume that your data is not static. You don't get your initial set of data, you put that in the table and you're done. So you typically have new data coming in and you are adding to the table. And so if I organize the data in a way and everything was great and then I append, I might be messing up with my data layouts. And so this calls out for this kind of optimization happening more than once, not only upon ingestion when the data lands in the Lakehouse or in such a table, but also regularly, because as I append, to the table, I could be messing up with the data layouts. Okay, so I've been emphasizing this example, the file skipping with min-max filtering. I argue that it can have significant impact. I mean, now beyond the simple example I provided, this has been shown in academic work. So there is this paper from Sigma 2014 on doing this efficiently and obtaining gains of 2 to 5 times, right, over a non-benchmark like TPCH. We have seen this in Qbeast with real use cases in real data, like a reduction of up to 70% of the amount of data you're reading. And probably one of the things that is crossing your mind now is, okay, so you're talking about this reorganization of data and reducing the amount of data I'm reading. Why can't I simply do Hive-style horizontal partitioning of the data? You can, and it's actually a great technique. There's nothing wrong with that. But if you try, if you look at the limitations of the technique, which often requires that you create like columns to do the partitioning right, because if you're trying to do over a column that has high cardinality, that doesn't quite work. You have a lot of data fragmentation. So there are techniques like the one I alluded to of the partition space that doesn't necessarily give you those problems, doesn't force you to like create columns or deal with funny organizations of directories in your storage. All right, so housekeeping of the data lakehouse, which is what I'm trying to convey here. So I don't know if the term is too funky, but to me, when I was thinking about all this stuff, the term housekeeping kept coming back because I see this as what happens when in my home, even when I'm a hotel here. So as your day goes by, you throw your shoes here, your towels there, and your dirty clothes somewhere else, and all of a sudden it's a mess, all disorganized, and you have to take your time to go and put everything back so that you know where things are and you're not stepping onto things and so on. But the housekeeping of a data lake house is not only about the data layouts. There are many things, but it's what I want to focus on this presentation. So for taking care of the data layouts, there are 2 parts of the data lifecycle, broadly, that I believe are important. One is the ingestion, when the data is landing into the lakehouse, and also over time, as you do appends and probably the layout has changed and you can improve, you can have a more efficient data layout. You can do it again, revisit the data layout and re-optimize it. So what I'm going to do for the rest of the talk is discuss one particular way of doing this, which is with this extension of Spark that we have developed called Qbeast Spark. It implements a multidimensional indexing approach based on an algorithm called O-tree. So it's a tree indexing approach where we organize the data according to that index. It's an open source project, so I'm putting down the URL here. If you're interested, by all means, go check it out, try yourself, contribute, discuss with us, whatever suits your needs. All right, so indexing with Qbeast Spark. So let's see what this is about. So the idea is I represent my data with a space defined by a set of dimensions. These dimensions correspond to columns in the table. Those columns I can choose. I can manually set, hey, I want to index with these columns, or I can use an auto selection feature that chooses that for you based on correlation. Once you have those dimensions, then we're going to go into this cycles of partitioning the space, trying to reach subspaces of a particular target size. Okay, a target size that I also choose. And the implementation, what the implementation will do is take this space representation and map that to a tree. Okay, so the nodes of the tree essentially correspond to the subspaces you see in that figure. So this is just an abstract view of what happens. This data structure is an actual implementation view. And as we get more records to index, we're gonna navigate through the tree and decide what is the appropriate place for that particular record. Now with that, we populate the individual nodes. So these individual nodes will contain a subset of the space. We call the subsets of the subspaces cubes. And once we have the cubes populated, then we map them onto files. So the ideal situation is that we have one cube per file. That's not always the case, as data is not always as we would like it to be. So it's not going to necessarily have partitions of the same size, and so I might end up with files where I bring together cubes with smaller amounts of data. Now, to actually do this is very simple. So if you can open, for example, your Spark shell and write a command like this. So I create a data frame, say, out of a number of Parquet files. Then from that data frame, I can specify the format being Qbeast. Then I can specify the columns here. I'm setting the columns manually. Then I choose a cube size, choose a path, and that's it. And it creates the table for me. The second part of the lifecycle that I mentioned before, which is the rounds of optimization over time, that can be done with an optimize command like this. You can open the table and invoke optimize over that data. And internally, so this metadata, how does it work? Am I creating a new format? No, I'm not creating an entirely new format. That's one of the interesting things about it. So if you look at how Delta how Delta Lake works, in particular how the metadata is generated in the Delta log, we have entries like this, right? When I'm adding a file. It has information like the path, size, and stats. I mean, we have been talking about stats like min, max, and so on. So I try to highlight that, right? So that's present in the Delta Lake specification. What we do, in addition to that, is to add these tags. So these tags add information about the cubes and the tree index. And so with that, we are completely compatible with the Delta Lake format. So we can do this. You can open a table as Delta and process it as such. So there's no need to rely on Qbeast on Qbeast Spark if you don't want to. Again, it's completely compatible with the Delta Lake format. And by the way, we have chosen Delta Lake to start with because we were working with Spark. But as you see, adding this metadata, there is no reason why this should work only with Delta Lake. In fact, we do plan to expand this to other formats. All right, so that's a very brief introduction to what a Qbeast Spark does. Let's now play with a bit of data, okay? Probably just like a half or more of this room, I have chosen the New York City trip record data set to play with. That is good for a couple of reasons. One is, well, it's public. Second one is reproducibility. I didn't want to come here and show you results with data that you cannot access. So I'm showing you data that you can go fetch yourself, try yourself, and see how it works for you. For this particular instance, I got the data from 2022 and 2023. That adds up to 24 files, one per month. And there are about 77 million records in the overall data set. For the experimental setup, again, to make things simple, I use this laptop to run the experiments. I use these software versions. And for the performance figures, I just collected them from the Spark UI. So this is pretty much a setup that anyone here can reproduce. And this is the schema of that data. It has 19 columns. They're all numeric. I have taken those files, I have ingested with Qbeast. I ran a command like the one I showed a couple of slides before. And once I do that, I can get the statistics like this from the table. I don't want to drain the whole slide because this is stats about the cubes and their sizes at different levels and so on. But I want to call your attention to 2 lines here. One is the target cube size. So I have chosen a target of 50,000 to start with. And I've chosen 4 columns to index with. Okay, so pickup time, drop-off time, pickup location, drop-off location. This first graph is showing the following. Okay, here on the x-axis, I have the values I find for one particular column I'm indexing with, which is pickup location. Okay, and on the y-axis, I am showing the normalized file counts for that particular value. And I'm showing for the Qbeast formatted data and the source. So we can see that there is a pretty significant difference here. With Qbeast, values are present in relatively much fewer files compared to the total, while for the data source, we have essentially all values present in all files. Now, the reason why I have normalized is because I have chosen a small target cube size. I have a much larger number of files with Qbeast compared to the data source. So let's keep that in mind for a second. I also did with another dimension, which is pickup timestamp. And this one is interesting because this particular column, the data here is very, very skewed. The natural timestamp for so the timestamps for the natural time for the data set is around this time here. And so that's why you see like a spike here. And pretty much a lot of this prefix here should be here in the first place. It's probably some error with the data, but I wanted to keep, I wanted to stay true to the raw data set, and so I just kept the whole data as it was. But we still see that, relatively, the values are in fewer files compared to, relative to the total and compared to the data source. So I then ran a few queries, filtering query, simple filtering query. I'm not doing anything else, and just seeing how fast it's able to do it compared to doing that against the data source. So I did a warm-up run, and then I did 3 different runs. I'm reporting each one of the runs, the results for each one of the runs. And we see that in each one of them, we were able to improve. That's not surprising if you look at the amount of data that we're reading relative to the data source. So we're reading less data with Qbeast compared to the data source, and as a consequence, we have higher performance. But of course, this is very simple process. I'm just doing a filtering over two columns. If I increase the amount of work I need to do, the fact that I'm reading less data will make more of a difference. So now, what I'm doing is, in addition to the filtering, I'm sorting and I'm asking it to return all the data for the first 20 records. So in this case, we see that there is greater benefit, right? So the query execution time is even shorter relatively to the results we get with the data source. And the same thing for the amount of data I'm reading, because now I'm not reading only 2 columns. I have to read all columns so that I'd be able to return the correct results. But this is not foolproof, yeah? In this case now, what I'm doing is, I'm saying I started with a filtering range which is fairly narrow. So with small files, that works pretty well. But if I'm interested in doing queries that have wider ranges, I'm expanding the ranges I'm filtering with. So if I'm expanding that, then at this point, Qbeast is not performing well anymore. And the point is, because I've chosen a small target size, I have a lot of files. And so if I expand the range, I have to read more files, I have to read more data, and so overall, the performance is not as great. To fix that, And this is to highlight the importance of choosing properly the target size, target cube size. So now what I've done is I have re-ingested the data source, and I have changed the target cube size. Now to choose this cube size and to be compatible with the source, I just took the average of the files in the data source, indexing with the same columns as before. So now, here's what I have. I did the same analysis, yeah, for looking at the distribution of values across files. So we see that with Qbeast, I still have values present in much fewer files, indicating narrower min-max ranges compared to the data source. So that's great. For timestamp, the situation is mixed, right? So for this prefix, this prefix of the data, so everything is good. The values are in much fewer files compared to the total. But when you get to this end of the domain, you see that those values are present in all files, and this is an artifact again of the skewedness of the data. But still, if I run queries against this, if I take the same query where I expanded the range and chosen a wider range to filter with, still see that overall I get higher performance compared to doing that query against the input data, directly against the Parquet files. And I'm also reading less data as part of it. All right, so with that, there are many more experiments that I actually have done, but I don't think I'll have time to cover them here. So if people are interested in looking to this, I'm more than happy to sit down and discuss further. But I wanted to give a sense of what Apache Spark does and some results of using a public data set against it. Of course, as we increase the size of the data, the complexity of the processing and so on, the results are expected to be even higher. So feel free to try on your data. I'm ready to wrap up now. So a few key takeaway messages. I argued in this presentation that there is great benefit in paying close attention to the data layout of the data you are putting in your Lakehouse. So in particular, I focused on min-max file filtering and optimizing for that when you are organizing the layout of your data. So we have seen that with our experiments that we can read 45% less data by using techniques like this, and even have a 50% shorter response time for queries. I also mentioned that this kind of optimization can happen in two broad parts of the lifecycle of the data. One is the ingestion, when you are lending the data, new data into the Lakehouse, and the other one is just when the data is at rest, but you are changing the table over time. You might want to revisit that layout to make sure that you're getting the highest efficiency possible out of your data lake. And again, I've used the term data lake housekeeping to refer to the housekeeping of the data lake house. Keeping your data lake house in order, trying to get the best out of it and the highest efficiency possible. And with that, I conclude my presentation. So here, ready for questions. Here are some links. LinkedIn if you want to connect. Otherwise, thank you.